All right, I think we'll just kick it off. So, welcome everyone to day 2 of the Understanding Latency webinar series. My name is Björn Everteigen. I'm head of research at Domus, and I'll be your host this morning, afternoon, or evening. So first, let's get the practical details out of the way. We have 3 types of sessions during the webinar. Each day kicks off with a keynote talk, followed by a series of panel discussions and talks. The panel discussions will be roughly half an hour, and each talk is 15 minutes. After each keynote panel or talk, we'll do a Q&A. So we invite everyone to ask questions. To ask a question, please use the built-in Q&A in the Zoom tool. Yesterday, we had a few questions in the chat. It's not that we won't necessarily get to those, but it's much easier for us to organize the Q&A if the questions are actually submitted through that system. So to increase your chances of actually having your questions answered, please make sure to use the Q&A tool. So yesterday, we covered what is latency and why does it matter, with topics like how latency affects applications and in turn end users, and why the time has come for ISPs and everyone to improve latency in their networks. The full recording from the webinar, all 3 days, will be made available to everyone who's registered. So do not despair if you missed yesterday's talk. And I also want to remind everyone that this will be a knowledge sharing event. The point is to share experience, insights, and best practices related to measuring and improving latency. This is about highlighting a problem space or opportunity space, if you like, that all of us have a shared interest in tackling in the best way possible. So with that in mind, I'd like to introduce today's program. So, yes. Today's theme is how big is the problem and what is being done to fix it. So we have several speakers covering topics related to measurements of latency in the actual internet and tools for doing that properly. And then we have several speakers covering topics related to solving the latency problem. Our first keynote speaker today is Kathy Nichols from Polaire. She's done a lot of past work in and is still opinionated about passive measurements, active queue management, and diffserv. She's currently securing limited domains. She's the one of the co-authors of the original paper that identified the buffer bloat problem, and also the Codal AQM that's part of that the solution for that problem. So with that, I'd like to invite Kathy to share your screen for the keynote. We can't hear you at the moment, Kathy. You're muted in Zoom. It worked earlier, I think.
Oh, there it goes.
Ah, there we are. Yes, excellent.
Okay, I was just saying when I go to share the screen, that PDF isn't showing up.
Maybe it was because I was still sharing mine. I've stopped that now, so try again.
All right. Well, other things are showing up. That's what's concerning me. It is not showing up. I don't know whether it doesn't like the PDF viewer or, let's see, could I open it in something else? It is absolutely not showing up. Let me try. Let's go to the front and try play. Okay, I'm going to try something else. I think this is how Zoom discourages you from using the browser.
Yeah.
Well, I did email you my PDF. Yeah, it's definitely, it would let me share. Okay, let's see. What could I do here? Yeah, it won't let me share Keynote or the PDF viewer. I'm on a Mac.
Okay. Maybe I found your PDF here, so maybe I'll try sharing.
Oh, okay, wait, maybe it'll do it now. I tried.
It might be necessary to share the whole screen. That's what some of the other speakers have done.
Okay,
There we
good.
are. Now it's working. Excellent.
Work? Okay, great.
Yay.
Yay. Okay. I don't know. I tried a different. Okay. All right. So I'm a late replacement for Matt Mathis. So I might be a little off topic. Plus, Matt is all about having a active global structure for measuring the internet, and I'm the opposite. I'm going to tell you that you don't need one, and that the truth is in what you can capture from the packet or the packet traces. And in that sense, I'm saying that, you know, measurement can be a subversive activity in the sense that you can go out and measure this stuff wherever you want, and you will have the truth of what kind of delay your applications are seeing, instead of what somebody tells you from an application that, or from a like a little active measurement thing that you don't really know what's going on with it. So all you really need is your laptop or some other device, some packet capture, and your brain. Don't forget to bring your brain, because you're going to need it. And I also want to say that this work is from like 6 years ago or more, because this isn't what I'm doing anymore. And the measurements themselves might be out of date. They predate the wide distribution of BBR and some AQM in the infrastructure. But the message that I've got here, I believe, is not. And I'm going to kind of go easy on the results, because I think, you know, they're kind of out of date, but you can go look them up in some other talks I've given before if you want to see in great detail what I learned 6, 7 years ago. So historically, when we thought about passively measuring networks, we did things like SNMP and net flow, and, you know, that's pretty crappy information. But really what we can do here is we can capture the packet headers, and then we get all the same information that applications get. And there's a lot of information to mine from the packet headers. And that information can be robust under sampling, and it doesn't really require that you have both directions of a flow necessarily, depending on what you're after. So my message is, don't probe networks, you know, don't get your cattle prod out there and stick them with active measurements, but instead listen to them, like, you know, just sample the packet stream. And that header information has sequence numbers, timestamps, and, you know, there's also the interchange of SYNs and SYNACs and so on. But when you've got that, you've got to make sure you don't miss anything, and you need both directions. And network engineers want to know the same kinds of things that transport protocols want to know about the network, right? They're trying to understand what's going on to the network, so I best know how to take advantage of this. I believe Stuart kind of alluded to this yesterday. And if you can analyze that packet capture information, you get to see everything the applications experience. You can cover all of the infrastructure that they've gone over, and you can deploy packet capture anywhere. And hence, because of these reasons, internet wizards like Van Jacobson have been capturing packets from the start, and that's what they use to learn about how networks actually work. So it doesn't work the way you think it does. That's a favorite expression around here, and it's a really great thing that you can find out, because if you actually measure the network, you may have thought that, oh, I'm going to put this great new congestion control algorithm or this great new AQM. But if you really go out and see what's happening, you get to find this out. And you shouldn't think of this as a bad thing, right? This is an opportunity. If it doesn't work the way you think it does, then your eyes should light up and you should say, well, this, what can I really do? How can I really affect this? So this is the beginning of wisdom, right? Not like a downer to say like, oh no, I failed. So here's the first thing I'm going to bring up about doing passive measurement, and this is quite simple. So everybody's interested in round trip times when they're doing measurements. And I'm going to talk briefly about passive ping as opposed to an active ping. Everybody knows about an active ping. You launch a packet out there, you get the reply back, and you take the time that you sent it out and the time you got it back. Well, with a passive ping, you take something from the packet. What I've used is TS vals, but you could use sequence numbers, and you say, you take the time when you see that go by, and then when you see it come back in the echo reply, but you kind of need to match them up and get the first one, you check your time then, and that gives you the round trip delay. Now you've seen the round trip delay that this packet stream is experiencing, as opposed to an active ping is you sampling the network. You're kind of probing this thing out and back, as opposed to you seeing what the application sees. And I just wanted to show one of the things that I did here was I was in a hotel and I said, well, okay, let me capture this and see what I can get. And of course, this looks like a hotel network, doesn't it? With this incredibly high round trip delay, and then it kind of drops down and then it goes back up again. But the minimum that I found to that same server was 11 milliseconds. So, it kind of gives you an idea of what's going on. And this was to an Apple server. And then here's like a Netflix server, and you can see the typical spikes that you get with video. And what they're kind of doing is, filling up because they like to burst everything out. By the way, again, this is old data. Netflix does a better job now. So to my understanding. But then, they just kind of blasted everything out until they started to experience loss. So instead of just capturing things on your laptop or your desktop, you can also deploy a box as a bump and a wire if you use it as a transparent bridge. And then you can kind of move your measurements around any place that you're able to put it. And this is kind of what I did, moving packet capture into the network. I took this little box, and here's an example of one place I captured in a house and put it in between the cable modem and the Wi-Fi. So now you can see what I've got here is I'm able to, if I take a passive ping this side, I can see the internet side delay, take it this side, and you get the home network side delay. And so if we take a look here, this side is going out to the YouTube server, and it's not a whole lot of delay variation there, right? That's the blue. And the yellow is the minimum that I ever saw, which was 88 milliseconds. So you can tell this, didn't have a CDN. And actually, this was in a second tier ISP and not from my home. And so that's why this delay is so long. Like if I take it from my home, I got a lower round trip delay here. But here's the home side. And of course, a lot of that is, various Wi-Fi issues. And over here, of course, I've only got 1.2 milliseconds as my minimum round trip delay. But, I'm getting all kinds of variation here. This is milliseconds. So, we even get up to 300 milliseconds. So, here's the problem, which is probably not a surprise to anybody now. So, but beyond doing that, the sort of passive ping approach, packet headers have even more stories that they can tell us. And here's sort of one way to think of this is, what if we put a capture point here between two hosts that are communicating? If we look at this first one and say it has sequence number 1000 and the next one has sequence number 2000, and we can measure the time between them, okay, now we can subtract the two sequence numbers and divide it by that time. And now we know that we have 800 kilobits per second on that link. Okay, that's kind of interesting. And we don't even have to see every packet of the return, and we don't need to see the return path at all. And then if, whoops, and we can also take a look at the TS spells and think of that as giving us sort of a low resolution time of packet departure from the sender. And in this particular scenario, we could say, oh, there must be some delay upstream of the capture point, because they would indicate that there was 10 milliseconds, but when we, we go in and subtract these two, right? We say, oh, well, they should have been 1 millisecond, launched 1 millisecond apart, but I saw them 10 milliseconds apart. And yes, I know there are all kinds of problems with TS spells, and I'll mention some more of them later. And again, you could look at longer talks if you really care about it. However, I still was able to get a lot of information out of them. But a thing I want to say here is, if you do this, your measurements are noisy, okay? I mean, there's no getting around it, but that's fine. We need to think of ourselves as maybe more as scientists, measuring things. If you go out and measure things on the network, you're going to see noisy measurements. It's just like when people go out and measure nature, they can't expect the same exact number, and they don't have to do anything to filter out the information. And also, this isn't as easy as running a ping, right? The diagnostic use of header capture means that you have to understand the underlying protocols. And of course, they're always evolving a little bit. And you need to have useful transport protocol headers, useful TS spells, and not everybody puts them in. Some people use 10 milliseconds and some people dither them. So, and you also need an analysis bag of tricks so that you can really hear everything that the packets have.
Kathy, sorry, something's up with your audio now. Last 5 seconds. Sounds like it switched to a different microphone or something. We can still only barely hear you now.
Oh, I see. This kind of went away.
There's still audio, but it's sort of muffled. Sorry?
It's still muffled now? I guess so.
Now it's better.
Okay, is that just 'cause I'm sitting close?
Still not great though. I can hear you, but not very well.
All right. Well, I don't understand why.
Yeah, it does sound like your microphone is somewhere else. Like, could it have fallen down or something?
Yeah, I think it stopped using, and it isn't showing up in the selection either. I have no idea why it decided to stop using the one that I wanted to use. I will try.
Now we can't hear you at all. So something's changed. Still completely silent now. No, we can't hear you now. Yeah, it might fix it if you rejoin the meeting or turn the microphone on and off or something like that. Still silent. Do you want to try just reconnecting to the Zoom? Do you want to try just reconnecting to the Zoom, or should we move to the next speaker? I can't hear you. I'm sorry. So if you're saying something, yes, yes, we'll do that. That's a good idea. All right. So thank you for the first half of your talk, Kathy. We will be able to edit the technical problems out for the recording, so that's no problem. Our next speaker is Toke Høiland Jørgensen. He will be speaking about Express Data Path, or eBPF, enhanced. Is it enhanced Berkeley packet filter? Extended Berkeley packet filter, I think it is. Tuke has a PhD on active queue management and packet processing in Linux, and he's one of the co-authors of Cake and a contributor to the eBPF XDP projects in Linux. So Tuke, with that, please, the stage is yours.
Thank you. Can you hear me?
Yes, I can hear you.
Awesome. Let's see if I can get the screen share to work as well. So did that work? Do you see? Yes, it says I'm sharing my screen, but it doesn't show it. So do you
It
see
is
this?
working. Yes.
Awesome.
Excellent.
Great. Okay. So hello everyone. I as Björn just said, I have a background in latency stuff and been part of the buffer bloat effort for a while now. But these days I mostly work on eBPF and HTTP in the Linux kernel as a kernel engineer at Red Hat. And I'm going to speak a little bit about this because it's a cool technology that allows us to do stuff that was previously hard or impossible to do. And some of this is also relevant for the latency use case. So I will start with a little introduction. Some of you probably know what eBPF is, and it's true that it started out as an expansion of the venerable old Berkeley packet filter, but these days we actually try to sort of avoid expanding the acronym because it's evolved to the point where it's better to think of it as a general purpose technology that just lets you run code in the kernel space. And what this does is that traditionally, like the Linux development process itself moves fairly quickly, as those of you who are familiar with it probably knows. But once we get out to the consumption point of the technology, it moves a lot slower, right? You can get new features in a kernel, but then it takes multiple years to for that technology to actually make it into distributions and the devices that we all use. And of course, this varies a bit. I work for an enterprise vendor, so that is its own ball game. But also, those of you who are familiar with the embedded space know that, especially home routers, by the time you buy a device from a manufacturer, it's probably already half to a full decade out of date in terms of kernel technology. So this means that sort of all OS level and kernel features take a long time to get from the development stage and into where we can actually use them. And so the promise of eBPF is that we can dynamically load code into the kernel and sort of increase the rate of innovation in the operating system space. And so just a brief run through of what eBPF is. Some of you would already know this. I won't go into excruciating detail of this, but basically what we can do is we have an instruction set, which is similar to, but not quite the same as the x86 and ARM instruction sets. And you can load code into the Linux kernel. And it will be just in time compiled to machine code. And then the Linux kernel provides a runtime environment where you can attach this code to event-based hooks all over the kernel. And you can have access to some kernel functionality via helpers and what we call kfuncs. So like we whitelist some functions you can call into the kernel. And then we sandbox the execution environment by doing in essence, static analysis on the bytecode, so that you don't the verifier will block the most common memory mistakes and all this stuff, so that it's safe to load in the sense that it won't crash the kernel. It will, anything you do that will crash the kernel will be rejected ahead of time instead. So with this, one of the hooks that you can attach to in the networking space is called XDP, which is the Express Data Path. The X means it goes fast. And it's this programmable layer that runs in front of the kernel networking stack, where you can do, you can execute your eBPF code right as on a packet as soon as it comes in from the network, and you can read, drop, modify, redirect the packet, and so on, with very high performance compared to what you could before, because we avoid memory allocations and there's some adaptive bulking. That means that you can get an order of magnitude processing performance improvement. And then because this runs inside the driver in kernel space, you still have access. You can sort of pick and choose which kernel functionality you want to use, and you can think of it sort of as a software offload running inside the kernel, where you can do interesting things with every packet that comes in. And this is just an example from the performance analysis we did when we wrote a paper on this. The x-axis is number of CPU cores, and of course you can see the 4 lines at the bottom is various ways of dropping packets on the regular Linux stack, where you just use IP tables in different modes. And then the purple line is HTTP, where we scale up to 108 million packets per second, which at this point is sort of, you're hitting the transactions per second limit of the PCI bus. And just sort of to give you an idea of how much is 108 megapackets per second, if you run at 100 gigabits these are like 64-byte packets, you are at 140 megapackets per second. So this is like minimum packet. So and like software packet processing, the challenge is packets per second, not so much bytes per second, which is why this is what we're measuring. So just to give you an idea of we have this sort of software fast path in the kernel where we can do this thing, and we can combine it with other hooks in the kernel and do interesting things. That's sort of the main thing here. And so how does this relate to latency? I'm speaking generally about what you can do with eBPF here. There's I'll go through a couple of examples of some real use cases we've seen where we can do interesting things with this technology. It's still there's some products and applications starting to be developed and distributed based on this, but it's still to a certain extent it's a low-level programming environment. So if you're looking for sort of point-and-click deployable solutions based on these are starting to emerge. And the examples I'll go through here are some examples of some real stuff we've done with this. But it's mostly to pique your interest and give you an idea of what can be done with this technology, rather than show you things you can install today. So one thing is, oh, I've switched the order and forgot to update this slide. Okay, so I will start with this one. One thing is you can use this technology to better scale your software stack. So one use case here is, we know that the Linux kernel has some of the best-in-class software queuing infrastructure in the QDisk layer, where you can install fqctl and shedcake, and you can do HTTP-based tree-based shaping and all these advanced features. But the problem with this is that the QDisk layer works by having a global software lock. So it doesn't, and since machines these days tend to be multi-core, you have trouble scaling across CPUs. So it's really hard to scale to high bandwidths and do this. And so this particular use case is sort of the ISP middle box type thing, where you have a per customer shaper. So you basically have the traffic is divided up between different subsets. And then what you can do is you can use XDP to redirect the traffic to different CPU cores, and that way, so that like you know that a certain customer's traffic is always hitting the same CPU core, And that means that you don't need global locking across CPUs anymore. And that means you can get pretty linear scaling across CPUs. And this is sort of the underlying technology of the LibreQoS package that has adapted the HTTP CPU map TC package that Jesper, my colleague, wrote to implement this. So that's sort of one way you can use eBPF to increase things. The other is passive latency monitoring, which Kathy just started talking about. So the nice thing about this, I won't repeat what Kathy said, but this idea of matching TCP timestamps and extracting latency measurements from a middle box is really cool. So the existing software solution that Kathy wrote uses libpcap, which works really well, but has trouble scaling past basically 8 gigabit on modern hardware, because basically because the kernel path is slow. You have to copy all packets to user space, and then you have to do the analysis there. But with eBPF, we can inject code into the kernel, and we can run it in the packet fast path, and we can do the timestamp matching for every packet that goes through the system on any middle box. And since most of your home routers run Linux, that's really easy to install that. And so I have a PhD student who's re-implemented Kathy's ping using eBPF, and which allows it to run with very low overhead and scale to 10 gigabits and beyond on a middle box. Then we have another interesting thing that we actually found while experimenting with the EP ping thing is that as I showed with the graph at the beginning for HTTP performance, Linux servers are increasingly connected to higher and higher speed hardware, and the per packet performance is the bottleneck here. And what happens is that if the CPU cannot keep up with the incoming packets, most network devices will have pretty big ring buffers on the RX side, which means that for one thing, you will get packet drops if your server can't keep up with the load, but you will also get latency because you get head-of-line blocking in the hardware before the packets even get into your CPU and into your server can process them. And what you can do to alleviate this is you can try to move the processing around so that you can, like with XDP, we can increase the number of packets per second that we can process, and that means that we can keep up with hardware at faster speeds. So we avoid introducing this head-of-line blocking, we avoid the packet drops, and so you can either do filtering, which is the link at the bottom in this slide, is Cloudflare does this, and have a public blog talking about how they use XDP to do DDoS filtering on every server instead of having a middle box, which is also interesting if you have like an edge deployment and don't have expensive hardware firewalls. You can sort of do the processing there, and that means you can drop all your excess traffic really early using HTTP, and then your stack can keep up with the thing. But you can also do something similar to the ISP middle box use case, where you move traffic around. So you decrease the amount of processing you do in the CPU that receives a packet, and instead you move packets to another CPU and run the stack there, which means you avoid the head-of-line blocking, because on the CPU you can do smarter things like apply queuing or AQM or what have you. And then the final thing is a sort of future-looking thing where we have this HTTP software offload path, which means we can increase the processing rate of Linux machines. And one obvious use case for this is the middle box thing, as I mentioned before. Also home routers, where we see hardware offloads appearing that don't necessarily handle buffer bloat and queuing in a good way. So with this HTTP software offload, we can actually process packets in software and do the right thing. However, currently HTTP has no facility to queue packets, schedule packets, anything like that. So we are working on a solution for having a programmable queuing mechanism built into HTTP, which will allow you to implement all the queuing algorithms you want and still have the performance benefit of HTTP as a software offload, which I'm hoping will allow especially home routers to scale, but also things like the ISP middle boxes and all this stuff. Just having more packets per second per call means you spend fewer calls, so you expend less energy in doing this and can still get the full programmable performance that you want. So just closing remarks, eBPF is sort of this technology that allows you to do lots of things, dynamically extend the operating system and sort of unlock the potential for innovation in the kernel, especially in programmable networking. And I'm hoping that you will think this is interesting and think of it as a possible solution for your application needs, also in networking and low latency applications. Questions?
All right, thank you very much, Toke. Yes, let's move to the Q&A. We do have a couple of questions. So the first one is thoughts on servers further breaking into the normal big metal areas of routers. I don't know what that means, so maybe you can explain what the question means if you get it.
Yes, I think so. So this is, I think the question is basically, can we do things on normal servers that we previously could only do on big metal routers now that we have this high performance networking? And I think we're seeing that happening already in the telco space, for example. A lot of like the whole area of network function virtualization, where you take the big box routers and you move them into software, is something that is happening. I don't think hardware, like in terms of raw performance, hardware is still scaling faster, and like you're not going to do 400 terabits on a Linux server, but you can do 100 gigabits, and for a lot of applications that is plenty. Also because right now available bandwidth is increasing faster than people can use it. So I definitely see this as a space. I don't think it will take over completely, but that is one of the use cases for BPF and XTP. And doing it in BPF allows you to go into this space, but still have all the kernel infrastructure like a routing table and neighbor resolution and all the annoying edge cases you can hook into the kernel, and then you can do your fast path in HTTP and get the high performance, which is sort of the selling point of this technology.
Cool, thanks. All right, second question is this technology getting attention from latest edge virtualization vendors for Open RAN, for instance, and virtual CMTS?
That is a very good question. I don't know.
Okay. And then I think we'll just take one more question. So what is the time scale for the queuing and scheduling in XDP?
That's a very good question. So I linked to my talk from Linux Plumbers last year, where we presented a possible solution. We got some feedback on things we need to change. So not that long, but I also hesitate to make any promises. But like, I don't know, some Linux releases out.
Okay, cool. Looking forward to that one.
Yes.
All right. Thank you very much, Toke. I think, Kathy, do you want to have another go at the end of your keynote?
Okay, can you hear
We
it?
can hear you now. Excellent.
Okay. Can you still hear me?
Now it's worse. the sound is worse, but we can hear you.
A little sound on my end, which means it did something. It changed.
Yeah, this is the same thing that happened earlier.
Yeah, it's like it's just changing on its own. Can you hear me now?
We can hear you sort of almost good enough.
Yeah, because this is from my box. Okay, what if I pull the box a little closer? How's that?
Sorry, I didn't catch that.
Can you hear? Okay.
I can hear you when you're sitting still. It sounds like the microphone is somewhere where if you're like moving, then it's noisy.
Okay, can you hear me now?
Yes.
All right, I'm going to give it a shot. I don't know why it just decided, I heard a little tone and it changed speakers apparently. So
Yeah.
let's give this a try. I'll try to hold still and stay up close to the, all right, here we are. I want the, what do I want? I want to share. Okay. There we go. No, that's not it. It's the keynote. There we go. Share.
Yes. Now we can see your screen.
Okay, so all right, so anyway, this was actually the stuff was very cool, but so now there's faster ways to get stuff. But what I'm going to now talk about is something other than doing the peeping and trying to get something out of that noisy data and try to convince you that you can actually do things with a single direction. So hold on, this is a little dense, but you know, you can always go back and look at it later. So the idea here is that you can get from a single packet, you can get some useful information in order to localize the delay. And if you think about it, every packet path has an intrinsic and constant propagation delay. I think we heard about that yesterday. And it also has a size-dependent store and forward delay. But the dependence on size will be more or less significant depending on the rate. So if we take those things as constant for a particular size, then we can say that the delay that any particular packet experiences is that delay variation or that queuing delay that we're kind of concerned about. And so let's kind of think about this. We've got a packet that comes into our capture point, and it has 3 times that are associated with it. And we can look the time that the first host sent this packet I, and that can be estimated by the TS bell. And the time that host 2 sent the packet that caused packet I to be sent, right? It comes in and sends another packet out. And the estimate of that is the echo reply time. And then there's the packet arrival time at the capture point, and that's just your local clock. So if we take those estimates, we can write these 3 equations and say, you know, these are the components of them. And so what I'm trying to tell you here with this red circle is that's our focus, that queuing delay. Because what we're going to do is, you know, bring that, we can say TS bell minus the echo reply is equal to that queuing delay plus a constant. And if we can kind of say, well, we can back out of that constant, now we can see the queuing delay. And then what we do is we look for observed minimum values, and we figure that's where the queuing delay is 0. Okay, so this sounds like a lot of hand waving, and it's really noisy, but I've worked with this and it works. What you can do, you can look at packet traces in other ways. You can compare it against the passive ping delays, which are actually a different type of measurement because they're only using the clock at the capture point. So yes, there is definitely clock skew. It's definitely an issue, but it's not insurmountable. And you can look at this work of Vern Paxson and Sue Liu, and you can look at I put some code out in open source, which is a not real well tested version of a proprietary code that I use to do all this work with. And the thing that I used is called TSD, Transport Segment Delay Estimator, and that's why you'll see this in these older slides. So here's the different estimates we can get if we've got these two hosts talking to each other and a capture point in the middle. We already know that we can, if we can see both directions, we can get this round trip delay with passive ping. But if we only have one delay here at the capture point, we can take the time at the capture point minus the TS val, and of course I have to do some math on it, and we get the delay variation from host 1 to the capture point. Then we can also compute the time at the capture point minus the echo reply time, and we're estimating this delay. But this is like a really noisy, crappy measurement. I never got great stuff with this, well, a few times, but so this is kind of a funky measurement. But this one gives you the delay from host 2 to host 1. It's the TS val minus the echo reply, and that's not bad. But this is the best one, which kind of makes sense, you know, and then this one could be a little noisier, and this one's very noisy. Then if you can see both directions, now you can get a lot of different, you know, you can get it in from both sides. Okay, so the other challenge, which I think you've heard a bit of from Toki, is, you know, you're getting a lot of data, and the data is coming in fast. And so that means you have to think about things that you can do on the fly if you really want to use this as an on-the-fly diagnostic. I mean, you can also save the traces, but even in that case, you can see that there's some issues. And this is just sort of, well, you know, here's an example of how you might, you know, the different pieces that you need to think about doing, but you also need to have a good bag of tricks. And I think Toki was kind of talking about part of the bag of tricks, which is certain things. But another thing that I like to use is getting statistics on the fly. And there's something called T-Digest, which is just great for that. And I just wanted to show here that the yellow lines are T-Digest estimates. This is post-processing a trace. And the boxes are the actual values. So, you know, it's doing a really good job in getting pretty close. You can also see some fun data here where this passive pings got really, really long. So I just want to say that's one thing you should make yourself familiar with. You can run it as the things go by. The issue with that is what I've done in these measurements is basically just kind of dump everything and start over again at different intervals, because I don't want to know the statistics necessarily all the way from the beginning, but I want to know, you know, what's happened kind of recently, or sometimes I want to know both things. And there are other ways. Probably you can overlap these statistics. It is a metric that you can add or subtract. So it would be that kind of a cool thing to do, is to kind of tile them so that you saw the change reciprocally. And sampling, all I'm going to say about this is you can sample. I tried it out, and this is just to show that it's even decimating by 100, things weren't too bad. So it's just another thing to think about. Then the next thing is to have visual diagnostics on the fly. And the first thing you think about is strip charts. And in this case, I'm running some strip charts, and you know, there's the downstream and the upstream, the downstream and the upstream. So you can see kind of typical of a home setup. On the downstream, it's getting pretty good performance. Although I will say, early measurements before demonstrated things, the downstream was not as nice as this. But look at this. This seems to be mostly what we think of as good Q. It's the median is right here about 3 milliseconds, and we're just kind of moving around a little bit. It's kind of good that we don't go to 0 because we don't really have starvation. And then the upstream queue, it's not terrible, but we are getting these peaks that probably shouldn't be there, and we are getting 50 milliseconds. Okay, so this one is a definite picture of bad queue, and it shows some other things that you can get out of the packet stream that I wanted to illustrate. And here I have what I've added are red dots for sequence space holes and black dots when you got out of order packets. So these are additional things you get if you start looking at the sequence numbers. So whoops. So look at that. So here's the, you can see we've got these incredible delays. And then you get this cluster of black and red dots, which, probably means things are dropping, which, here we've got 600 millisecond delays. And this was in a hotel, and, there's lots of bad queues, so none of this is unexpected. But, back to this subversive activity, you can find out, just you and your laptop, that there is, not just that the performance is crappy, but it's not just that there's a bad network, but whoever's sending you data is not is not thinking in how they're deploying their transport. Okay, here's another visual diagnostic on the fly. And I'm not saying any of this is the way to do it. The reason I'm putting this out is what I hoped years ago, and I still hope, is to inspire people to go out and figure out what can I squeeze out of these packets and how can I display it. And this was an animated delay topology, and you can see here what I did was I would change it every 3 to 10 minutes, and this is the median delay variation was these red lines, and then I did the inbound delay variation on the top and the outbound delay variation on the bottom. And this is the delay distance from the capture point. And then I tried this other thing where the the size of the box had to do with how much data it was getting relatively. This is a delay topology map for p-ping, and here I've got the gray is the over the entire time, it's the statistics, and then the yellow is a shorter term, it's for over 10 seconds. And you can see here, you've got the round trip delay from the capture point, and the upper one, of course, is going on the away side towards the server, and then the lower one is the more local side. So a thing I want to leave you with, though, is, well, what delay do you think active measurement would see in this case? And here it's, this is some video over AirPlay using an Apple TV. And, I zoomed in here, and you can see the characteristic sort of spikes of the audio and video, and they're spaced apart. And during that totally idle time, if you hit that with active measurement, it's going to see an idle link. But if it hits on the spike, it's going to see something else. And if you look up in the corner, I blew it up some more. Inside a spike, you can see these little ramp up kinds of things. So again, ask yourself, what would you learn about this network with active measurement, with pings or something? And what will you learn if you actually look and see what's happening? So again, some final points are, if you were to probe a really crappy link, like a third world link, it's like a bad idea because you're now picking up some of that link with your packets. And also, you can get all this great information out of the headers, and then you can go ahead and mine this data for more information. So things to look out for is Google had done some work, and apparently Microsoft's signed on also in extensible timestamp options, which would have been really cool. You could have millisecond timestamps, but it seems to be languishing with the IETF. And if you are to encrypt packet headers, it will be hard to get information. Not impossible, you can probably do something. And I just wanted to note again that TS spells can be unused, they can be coarse-grained, and they can be dithered, so they're not always useful, but you know, you can usually find something to do a passive ping on. And this is just some links, talks, a longer talk talking about the data and the slides. Also, if you're interested in good Q and bad Q, you might, that site has some links to Dan's original talk and our paper in the UFC. And then about clock skew, you can look at these papers. You can also look at the techniques I used in this code. And the current work, well, you already know about some of it. And Dave and Toke gave me these links. And then if you get the slide deck, there's just a couple of fun pictures afterwards of a really crappy network. So like that. Okay, thanks. I'm really sorry about the sound. I don't know why it just.
Thank you very much, Kathy. I think in the interest of time, I think we just have to skip the Q&A. So sorry about that. And thank you again, Kathy, for an excellent keynote. It sort of worked out, didn't it? Because the part that was relevant for Toki's talk was before, and now we're going to the measurement people. So so that's good. So our next session is a panel discussion on latency measurements in the wild with Dan Seaman, Peter Thompson, and Lai-Yi Olsen. Yes.
Yeah, Lai-Yi, thank you.
So I'll let you guys introduce yourselves because my first question is what kind of latency, where are you working and what kind of latency measurements are you working with? So let's start with you, Dan.
Yeah, hi. My name's Dan Seaman with Perseem. So we've actually, it's great watching Kathy and Toke's talks because we've been doing essentially the TCP tracking for latency measurements using HTTP BPF since about 2018. So so definitely something that works really well. We basically use that to help internet providers understand the quality of experience that they deliver to their customers, and latency being one key metric to do that.
All right. Peter, how would you answer that question?
Hi, so I'm Peter Thompson. I work at a very small company called Predictable Network Solutions, and we use very fine-grained or forensic latency measurements to help our clients, typically telcos, figure out what's going on in their networks. And we get a lot of insight out of that, and we've been doing that for about 20 odd years now. And some of the approaches that we use, we've now brought into standardization through the Broadband Forum, and other people are also starting to use them, which is great.
Cool. And finally, Lai-Yi, what kind of measurements are you working with?
Hi, yeah, I'm Lai-Yi Olsen. I am the lead data scientist at Measurement Lab. We're a fiscally sponsored project of Code for Science and Society, and we focus on publishing open internet performance data. So all of our tests run TCP info as a sidecar service, as well as for NDT, which is our speed test, also uses TCP info to get RTT measurements, and that's how we get latency data. And another thing to note is that all of our servers are in interconnection points, but increasingly, or as of late, we've also added cloud servers as well.
All right, cool. So so we've heard a lot about sort of buffer bloat and other sources of latency from some of the other speakers, and I want to put it to you guys. So, how common are these latency issues in the networks that you are measuring? And I think each of you are looking at very different data. So, I'd really like to hear everyone's opinion on this one. Who wants to go
Please go
first?
Yeah, I guess I can
go
first.
Dan.
Yeah, sure. So our customers are mostly like regional internet providers. That's specifically who we're targeting, and especially on the fixed wireless side. Although we do see some DSL and fiber and cable and stuff as well. And yeah, these problems are everywhere. But, I mean, mostly in the access network, and sometimes in the backhauls. Depending, we tend to find like the larger the provider, the less trouble they have with backhauls. It just kind of seems to be like a scale thing. But certainly overloaded access points, and then of course, if you go all the way down into the home, it's a huge problem there as well. So yeah, we see it all over the place.
Yeah, I can answer the question in a bit of a backwards way. So part of, like I mentioned, we publish all of the data that we collect. So a big part of that, the reason that we do that is because we want to ensure that policymakers, network operators, consumers, everyone can be looking at the same data set and the same sort of calculations for how we got that number. Our most popular test is our network diagnostic tool, which, as I mentioned, uses TCP info for RTT measurements, but people often are drawn to the shiny bandwidth throughput measurement that it returns in terms of the speed test. And so what I can say is our latency measurements are actually pretty unexplored. I would definitely recommend anyone on the call that's interested in taking a look, please do, because we get something like 4 million tests per day globally. So there's a lot of data there. And it's been consistent over time in terms of the instrumentation that it uses for the measurements. But in any case, my point being that a lot of people take our test hoping to get information from the throughput measurement and are confused because they'll get a number back that is quite high, but still be having a crappy time on their Zoom call or what have you. And so I can just say that I don't know how pervasive the cause is, or in terms of it being latency, but I do know that the emphasis on throughput has been a confusing part of the conversations within policy in terms of we're regulating this notion of speed without a clear definition of what it is, and if we don't bring in latency, it often doesn't totally answer the question. So it's not completely answering your question. I don't know how common it is. I don't have a way to quantify that at the moment, but I think I know that quantifying how throughput is doing is not answering all the questions. And so of course, then that's why we want to focus on latency as well.
Cool.
Yeah, so I would say from our perspective, latency it kind of is the universal issue, because the thing that you could never get back is time. So anytime a packet gets delayed, you can never undelay it. There's no solution for that. And just to say, when we think about latency, we're always considering loss as well. We don't really consider them as separate phenomena. They're two sides of the same coin. And equally, if a packet is lost, you can't unlose it. You can retransmit another copy of that packet, but from the point of view of the network, that's a whole new packet. So yes, issues with latency are universal. Issues with excessive latency are very common, and I would totally second what Liu there was saying about the focus on throughput has confused. I would say it's confused the whole industry. And I can see reasons for it. You can see the white beard here. I'm old enough to remember the days when we had like 28 kilobaud modems, and I remember the exciting day when we went up to 56 kilobaud modems, and there was absolutely no question that was totally twice as good as having a 28 kilobaud modem. Everything was better by a factor of 2, with no exceptions. So it made sense back in those days to think in terms of that number. The maximum baud rate that you could get, and making that better became the focus of the industry. And we finally moved away from modems. We got to DSL, and there was a lot of progression. And at the time, this was also improving latency because at 28 kilobaud, most of the time delay is serializing your packet out with those squawks, and actually the once it got into any remotely high speed part of the network, it never saw another packet. In those old days, speed and latency were very closely correlated, and it was the direction the industry was going was all good. What we see now is that in a lot of the areas where we work, there's a tendency to optimize for throughput in a way that can pessimize for latency. So we're in a difficult situation now that because everybody's become so addicted to speed as the measure of all things, and this applies to customers and it applies to regulators, and even though a lot of the industry is wising up to the fact that actually more speed, we're getting real diminishing returns, and I think Gavin Young mentioned this on his introductory talk yesterday. It's while a 56 kilobaud modem was really twice as good as a 28 kilobaud modem, a 2 gigabit link is not twice as good as a 1 gigabit link for practically everybody. In fact, the difference is going to be very difficult to detect for the vast majority of applications. But everything experiences latency, and indeed even the speed test is vulnerable to latency. When we work with clients and we work with big operators, and they're having a problem with speed test, and their customers complaining that they can't get the gigabit they paid for. The problem is nearly always latency.
Yeah. So
TCP works. So even though you think what you're seeing is a speed problem, what you're really seeing is a latency problem. It is everywhere.
And this is something you've been working with, right, Dan? Because you're exposing the latency measurements to the ISPs that buy your products, if I'm not mistaken.
Yeah. So exactly, and I think maybe the surprising thing, and probably the people in this audience already know this, but latency is such a valuable metric. Like if latency is good, almost always everything else is good. It just turns out to be very predictive of the overall experience. So yeah, so we use that as one of the key metrics. One of the things that Peter said there is interesting though, is that unfortunately customers do still value throughput most, just from a marketing perspective. They don't understand. Right now I'm at a conference for fixed wireless providers on hotel Wi-Fi that has 500 milliseconds latency under load, by the way. I tested it before I started and it's awful. But even talking to everyone around here last night, they say the same thing. I can offer 100 meg plan with good latency, but the marketing numbers, the gig is what people want to buy. And people are really struggling as service providers how to communicate the value of the latency. So yes, I think we've done, on our side, a good job of teaching people they can operate their networks by using latency as a key metric. And that's probably the main thing that we do, or one of the main things that we do. But teaching the customers to value it is a whole nother problem.
Yeah. Yeah. So, and all of you have experience building or running or using the data from large scale measurement systems. So perhaps you can talk a little bit about what are the issues or problems that you encounter when building or using those kinds of large scale systems. Perhaps you can jump in on this one, Lai.
Yeah, I mean, how long do we have? I think it's a good question just to point or talk about, why Measurement Lab was created in the first place was, to try and address some of the problems that were the reality at the time, which was in 2008, which was, being able to measure at scale in the wild, as well as sharing large amounts of data. So I think we've done a pretty okay job at doing that. It was something like 700 sites worldwide, and publishing the data in BigQuery, enables a little bit easier access for such a large data volume. But there's still many challenges, and I think one of them we can probably all relate to, and it's just a measurement challenge generally, which is you want to make sure that the signal you're providing is a symptom or is indicative of the network versus your instrument. So, being able to ensure that the network is the bottleneck and is the thing that you're actually measuring is a consistent challenge. And with that, I think I think there's always a sort of dialogue around if the metrics that we're collecting are the right ones, and but how to balance that with also wanting the desire and the need to create longitudinal measurements so that you can actually be able to compare data across time. So that's this kind of like, are we measuring the right thing is a really good question, but also is it worth changing it such that, our data is not comparable, across time and at scale. So that's a challenge. And then, I think also, as with anything, like the communication of the data. So a big part of what we're thinking about is, of course, we know that people will come to test the throughput, but how can we sort of prioritize the latency measurements just to call attention to it more? And, again, a big part of why we publish the data is such that policymakers have access to something that other people are looking at as well, and where they can see the open source calculations. But so all to say, informing those conversations or sort of influencing those to be more latency focused and do prioritize measurements beyond just bandwidth, trying to have the conversation steer in that direction, I think is a higher level challenge of providing
totally
this
agree.
kind of data.
Totally agree about that. How do you know that you're measuring the right thing, though?
I don't know if we do. I mean, I think what we've really tried to do is focus on the longitudinal nature of the data. So really being able to say how the internet has evolved over time. I think that's one vector of what we need to be looking at. And then I think what we've actually had a lot of luck with and seen a lot of success with is people doing local data collection. And so I think there's a real opportunity there to be maybe more creative, shall we say, and what kinds of metrics are being collected in terms of a variety. So I think, that's also something I was going to say to the last part of the conversation is I think it's interesting to think about measurements, the same measurement being taken in different networks such that you can compare between them and maybe get more insight into how a network is performing just by pure contrast of how others are. And so my point being, even if we have this kind of baseline of the global data, meaning our public data being collected, but I think if you have questions on the local level, you can start just taking multiple measurements and start thinking about, start comparing them. And the question of are we measuring the right thing becomes not less important, but you have more flexibility in how to answer that. Whereas at the global level, you're just wanting to kind of consistently measure the same thing.
I think on the question of measuring the right thing, from our perspective, we get some confidence that we're measuring the right thing when the insights that it delivers are useful to the people that we're doing the measurement for. And so this is where we find doing quite what can I say, fine grained, very kind of forensic latency measurements where we look at the passage times of packets at multiple points, and we're not, we're also we separate that into each way and not just round trip data, and then further segment that into what's happening on each network segment and so forth, and then also look at the how latency varies with packet size, which isn't always as linear as you might expect, and what's the absolute minimum delay you see, and all of these things have behavior which frequently isn't what you expect. For example, you might think the absolute minimum delay that anything experiences is going to be a constant. But actually, when you observe that over time, and as you were saying about longitudinal data, if you measure this, the same piece of network over a period of time, you very often observe things change. So, and typically, for example, minimum delay will sort of flip between different values over time. And that's indicating, probably there's a routing decision being made, and packets are being routed different ways around ring networks and stuff like that. You can start to see a lot of influences of the structure of the network and ways that things have been implemented that come out in this latency data. You can if you pay enough attention, you really can learn a lot. Back to your original question about large scale deployments. I mean, our deployments are typically nothing like the scale that Lou is talking about. But we are working at the moment with one customer who's interested in. I mean, we work with notwithstanding all the stuff that Kathy just said, we actually work with active measurement. So we typically use small form factor probe devices that actually reflect packets back and take timestamps and so forth, just so that it's all kind of under our control. And we're looking at a system of deploying up to maybe 9,000 of those across a network. And the sort of problems that you get are in being able to deploy things at scale. You need a lot of automation. You need to be able to kind of generate all your config files automatically from data that you're provided with already. You need to be able to kind of deploy and manage all of those things. All of those become quite large challenges. And the other challenge is the volume of data that you can produce. And where do you put it, and how much does it cost you to keep it? People sometimes make the mistake of saying, "Oh, we'll just store it all in Amazon," and then you get the bill back for keeping that number of terabytes for that number of months, and you don't like it. So then you get questions about, can we find ways to compress that data? Can you kind of subsample it or winnow it or produce digests of it or things like that of your kind of old data, so that you don't just kind of consume the world's SSDs in piling stuff up. So those are some of the challenges that we're aware of.
What does your Amazon bill look like, Dan?
Yeah, well, it's Google Cloud and it's scary.
Right.
Yeah. So, two things there that are interesting. That the comment of comparing is across customers is really important. So we take basically all the data and combine that together from our customers, and we use that to feed back best practices and comparisons, so they can see how they're doing versus each other. So that really does have a lot of value. And sometimes just having something to compare against, even if it's not a perfect measurement, is more valuable than a perfect measurement. But yeah, it's all about the cloud. We're primarily cloud based, and it's quite expensive. Google bill is not cheap. We track basically latency measurements every 10 seconds, like a histogram for every IP address every 10 seconds, and pump that all up. And it's billions of those a day. And it's so we do a bunch of things. We store them in Parquet files. We aggregate the Parquet files over time. We have them in other time series databases to power the real-time dashboards, and kind of same thing where they're compressed in time after a little while. Typically, you don't need to have like 10-second samples back a year or something like that. So we're able to compress that down. But yeah, it's a ton of volume, and it is not cheap to store that stuff anywhere.
All right. I think in the interest of time, we are going to have to end this panel on that note. So thank you to all of our panelists. And to summarize, I think our panelists who have lots of experience measuring this stuff all say that latency problems are everywhere. If you have to sum it down to one sentence. Right, thank you very much. We will have a 5-minute break, and then we will continue with our next speaker. So we'll come back at 17:28.
Given all the problems we've had, Bjorn, I would like to actually quickly test to see if my setup's going to work. Well, if I sound great, but can you see my slides? Start the slideshow. Bjorn, will you let me see if I can see my slides? All right, I will test later. I will trust in the winds. But anyway, you'll hear like a musical interlude.
Yes, Dave, please do that.
Well, at first you have to hear me tune up. I'll mute that.
You have 2 minutes, so you have to be quick.
Oh, would you like a punk song about the end of the world? I'll take good night, just out of sight. There's a star overhead, and soon we'll be living in the down in Santa Cruz, turning corn to goose, living in the Easter Island. Puka turns to man with your technology. Are you with me? So you'll be living down in Santa Cruz, living in the down in Santa Cruz, living in the
All right. Thank you, Dave.
punk
I'm
song.
I'm so glad we haven't gone corporate yet. I love this. All right.
Bjorn, would you let me test my slides? So I'm trying to share them and
They
I
are
don't see,
working. I can
I
see
don't
them.
see them.
You don't see them. I see them.
No, terrific. Then we'll just go from there.
Yeah.
Let me unshare them and hopefully we'll figure it out. Great. Bye-bye.
Cool. All right. So our next speaker is Cohen the Shepherd from Nokia Bell Labs, where he's the research department head. And he's also one of the co-authors of the L4S standard. So please, Cohen, the floor is yours.
Yes, hi, thanks, Bjorn. Let me share the screen first. Make sure I have the right.
We cannot see your screen yet.
No, I still try to find it. I hope
There we are.
this is the right one.
That seems to be the right one, yes. Everything's working, so.
Okay, so thanks. Thanks for the invitation and welcome to this talk about L4S. So I'll try to introduce shortly what L4S can bring in terms of latency, but also why L4S is so important for low latency service deployments. So I can progress to the next slide. I'm glad to see that more and more people realize that L4S is really a key component to provide low latency, especially towards a large user base. Once you know LFRS, the question is rather, can you even deploy a large-scale low latency service without LFRS? So for those that never heard about LFRS, the 4 L's in the acronym mean low loss and low latency, and the S is for scalability, for throughput, yes, but also, as you will see, for network deployments as a whole. So LFRS is defined in these 3 IETF RFCs published in January this year. And with these RFCs, the IETF has finally given the mandate to deploy LFRS on the internet, which is good news. First, I want to talk a little bit how a low latency service is typically rolled out today. So there we have 2 major components that need to agree on several aspects. On one end, it's the network that needs to make sure that it provides at all times a promised capacity, and failing on that has immediately results on loss, latency, and queuing growth. Then next to that capacity guarantee, the network needs to guarantee some maximum packet latency and service reliability. And finally, all these promises have to be carefully coordinated and assured throughout the full end-to-end network path. On the other hand, we have the applications that, of course, also need to know and respect the agreed capacity and promise never to exceed it. Actually stay far enough away from that enforced capacity limits, because as a true low latency interactive application, you don't really want to hit the policer or the latency wall. Also, wireless networks are very popular, as users today don't like to be on wires anymore, but wireless networks are even more challenging and bring additional user concentration and coverage limitations, making it even harder to keep promises. Also, if a user needs multiple applications, it becomes quite complex to make sure that the total sum of the throughput will never exceed, as agreed, the agreed capacity. So for some use cases, that might work because it sounds quite pretty complex and upfront arranged. But for the whole internet, that's another question, right? Let's be realistic. How will this ever work for multiple independent network segments and for non-related applications? And well, actually, that's where LFRS can help a lot. So looking at LFRS, it's a very, let's say, dynamic, real-time, in-band collaboration between the network and applications. And in the past, without LFRS, or still today, actually, the collaboration on the internet was pretty limited and has been grown kind of organically. Each end tried to improve latency from its own perspective without the help of the other actors. As a result, all mechanisms are based on implicit signals and often pretty advanced guesswork. So apps use, for instance, Cubic in this case, as you can see, that relies on the loss signal and can't keep latency low if the network has buffers. BBR goes a step further. That also takes into account delay and latency. And for big buffer bloated queues, BBR can definitely drastically reduce the latency in many cases. And then also we have the networks that try on their end with AQMs find the compromise between queue sizes and packet drop. And all these, you could say, one-ended mechanisms have to assume often worst case conditions that result in medium or sometimes even bad performance. As you can see, there's a lot of fluctuations and variations in queue sizes, in flow sizes. So it's not that optimal situation we are in today. With LFRS, we had the opportunity to define in IETF a truly collaborating mechanism from the start. So it involved both the network and the applications, and it is targeting actually the maximal achievable benefits. As you can see immediately, flows are very smooth. Queuing latency can be avoided completely, and the common throughput limit is fairly and smoothly shared. And this sounds probability too good to be true, right? But well, it's you should try it out. What's more, each actor can improve independently without harming the existing thing, but you definitely have to argue that you can only get a benefit if both the applications and the network are updated. But isn't that the case for every low latency service deployment? You have to change quite a lot, right? So I would claim that the better insight is that supporting LFRS makes your low latency service deployment only easier and better. Know that both Cubic and BBR already have been augmented to support LFRS. The PRAC requirements as defined in RFC 9331, and PRAC is kind of an improvement of the existing congestion control mechanisms that completely removes all the reasons why the network would need to create latency or loss on purpose. So while the old congestion controls actually need queue buildup to work well, networks can't blame LFRS applications for having a queue buildup or having packets dropped. That blame will only be due to the lower link technologies that the network is made of. On the other hand, any network link layer technology improvements on latency will finally have a direct user experience impact for LFRS applications. Without LFRS, low latency efforts were often lost in the required queue buildup if rate control was needed. So finally, we have these two worlds, one where packets get queued in the network, but still has many advantages for networks, and one where there are optimally no packets blocked and queued at all, which is great for our low latency interactive applications. So it's a matter of give and take, where having both in parallel can still be a win-win for both actors in this case. So there are many ways to make both coexist on the internet. So for instance, in RFC 9332, which defines a dual queue coupled AQM, that's actually only one of the options. In ITF, it was made sure that a complete unmanaged internet service would work correctly and properly, but definitely never let anyone tell you that your whole network needs to be upgraded with coupled dual queues. That really doesn't make sense. So as LFRS can help in so many ways, let's quickly go through this overview. First, the applications can tell the network which IP packets need low latency and support LFRS. Via these packets, the network can tell the applications the capacity that is available. With that information, apps will be stable, smoothly, and accurately controllable to any rate without the need to block and queue, drop or drop packets. Then smart networks will try to avoid blocking or dropping the packets at all. And if a lower layer technology really needs a bunch of packets together anyway, it is still possible to tell the application the queue size that it needs via the same mechanism. With LFRS, the network can give immediate and very frequent feedback. And it will give the same feedback, the same frequent feedback to all packets, especially in the bottleneck, without the need to know the underlying applications even. So all that will make the applications share the throughput evenly with other applications on that limited bottleneck throughput bottleneck. And yeah, just for a comparison, listed here, what are the limitations today with the existing? So we need queue. There are a lot of guesses that need to be made. Also without LFRS, the network needs schedulers and shapers to build queues. And they can only give a rough and very low frequent loss signal that actually also needs to be averaged and slowed down as the loss. They have to slow down that loss signal for stability. Now going back to our introduction, let's see with what we've learned here, how LFRS can make it easier to build a robust low latency service. First, with LFRS, networks don't have to worry that much about throughput guarantees. If you cannot provide all the time the promised capacity, it's not an immediate critical problem. If the network friendly asks on time to reduce the capacity, with LFRS, users will not experience latency and hardly notice the related quality reductions. Users are focused on interaction for low latency applications anyway, and feel great if they feel being in control. On the other hand, losing control and getting detached from the workflow is very irritating. We all know what effect that gives. It's very frustrating and in some use cases even dangerous. Also, with LFRS, applications don't need to know upfront the available capacity. A good LFRS network will allow the app to smoothly search for that capacity limit and later being dynamically guided without latency or drop penalties. Users also understand that the resources need to be shared at unexpected locations where the user density increases. And with LFRS, it won't impact the latency. So no user frustration. And if it's really too much of a crowd, users will find a better spot anyway, you could say. The same for rural or distant places. A few megabits per second and even less are surprisingly sufficient for staying remotely in control. And again, with LFRS, there is no need for a low throughput to have any impact on latency. And if users need more apps, they understand that the capacity needs to be shared. With LFRS, apps will smoothly and equally share and adapt to the available capacity. So there is no need for coordination. Also, more capacity, the more capacity is offered, the more apps can be used with a better quality. Users that don't mind the lower quality can still use the service and even could ask the applications or the network to differentiate the share. Also forget coordination between network segments. Every segment or even network node can independently reduce the capacity of flows to local limits. Just make sure that under normal conditions, you have enough throughput capacity to make your users happy and that you can avoid queue buildup in the LFRS way. So I hope you agree that LFRS is simplifying or at least taking away a lot of worries. And what is left at the end is the true networking latency, which can be the focus again and makes it worthwhile to improve without the risk of it being spoiled by buffering. So if you still have to deploy a low latency service without LFRS, then I wish you good luck, definitely. If you understand the power of LFRS and are convinced, like so many others, then I hope to meet you soon at Nokia or maybe in one of the LFRS interrops organized regularly during ITF and at Cable Labs. Thank you very much for your attention. If you have questions, feel free.
Thank you very much, Koen. We do have a couple of questions here. So the first question is, can an LFRS aware network element compensate buffer bloat of another network element that's in line, but which does not have LFRS awareness?
Definitely not, of course. Latency can't be undone. But there are a lot of worries about, let's say, what's the impact? And like I said, there are easy ways to support low latency. If you have to support low latency anyway, you have to make sure that end to end you can support low latency, right?
Right. And the second question is for L4S support in the network for some applications, does the service provider network need to support L4S on every hop, home CPE, access network, metro core network, etc., etc.?
Well, L4S, yes, as long as it's a bottleneck and a potential bottleneck. But again, yeah, it's today we have already deployed low latency services, which are typically kind of managed. I think the opportunity of L4S is there that we can reuse these services also for greedy traffic now, and control these mechanisms with the L4S way, let's say, so that they can be combined in existing paths which are already often there, capabilities in networks which are already there. L4S only makes it possible to also, let's say, rate control those greedy services on existing mechanisms in the network.
Right. All right. And I think the final question will be, are L4S, is L4S implemented in the mobile ISP equipment from Nokia?
That's hard for me to discuss about. That's a question rather to the product people, and definitely if network operators are interested in implementations, they can contact the Nokia business divisions, let's say.
All right. So thank you again very much, Koen. And we will move to our next speaker, who you've already seen on today for the musical interlude, Dave Tott. He's a buffer bloat legend and the co-author of FQ Coddle and Cake, and chief science officer at LibreQOS, among other things. So please, Dave, the floor is yours.
Thank you all for having me. Can you see my slides? Yes?
Not
Say yes.
yet. Now it looks like it's working. 2 seconds. It's still loading. Starlink is having
I fear that I'm going to have that problem today. I mean, I wanted very much to record this moment in history because I started on an acoustic coupled 300 baud modem. And here I am trying to come to you live via satellite.
Yeah, try to turn it off and back on again, because it says that you've started screen sharing. Yeah, there we are. Now it's working. Okay,
Oh, I just
you just need to enable it again.
All right, here we go. Oops, wrong thing. Share screen. Misunderstanding. Here we go.
There
Is
we
it
are.
coming through?
Yep, it's working.
All right. All I do is I see your text on my screen. I don't actually see my stuff. So anyway, technology. I got 15 minutes to do a 40-minute talk. And I'm going to try really hard to fly through this. There is a zillion links in the talk. Okay. Been at this for 32 years working on the audio side. Everyone knows this. Because this has been such a difficult problem, I have a sense of humor about it. And I try to explain things really simply as well as really complicatedly. Click on the links. Quiz for the audience today. Feel free to fill up the chat. Okay. Take a guess at what each of these 4 Q links is actually demonstrating as the TCP behavior. Okay. There'll be a quiz later. Most of my work was involved in itty bitty little routers like these things until fairly recently, and I decided to move up the stack into network function virtualization as well as middle box stuff, and analyzing what real residential traffic looks like. And it turns out that the typical web page is 3-second burst. A download needs infinite bandwidth, but almost everything else needs next to nothing. The biggest user is movie streaming. And chat is kilobits, video conferencing is 1 to 4 megabits. But there's constant little things happening all the time. Everything from little spell check lookups. And these are all the things that affect your quality of experience. So I've been able to gather some data from the ISP perspective in the last 6 months. And the numbers turn out to be really interesting. At customer peak, Friday night, 5 megabits per second average per customer of the people of the total number of customers of the people that are online. And only 2.5% of all residential customers plans on all plans crack 32 megabit at any given time. Really remarkable number. So it turns out on residential networks, once you have enough bandwidth, you hardly ever use more. There doesn't even seem to be a correlation between the number of people in a household. 50 megabit plans are pushing 26 to 34 megabits, and a gigabit plan about the same. So it turns out that for customer satisfaction, for the gamers and the video conferencers and day-to-day usage, what really does seem to matter more is consistently low latency, low mean times between failure, low mean times to repair, and something that just works all the time. Bandwidth is a lie. That said, we can achieve today with technologies shipping these kind of results for low latency all the time on at least most of our traffic. So by the way, as a quick question, all those slides get through this time, Bijan? Yes?
Yeah, I've seen all your slides.
Okay. So the other problem we see in residential networks is 97% of all residential access ends in Wi-Fi. Nearly all ISPs say that Wi-Fi is their biggest problem, and there's 18 billion Wi-Fi devices. Yet we don't have any interoperable events. There's 6 different versions in the field, and there's very few people investing directly into making Wi-Fi better for everybody, except it seems my project. We see a lot of activity now on Wi-Fi 7, which is great, but we have to interoperate with Wi-Fi 5, 6, 4, 3 in order to have our networks continue to scale properly in residence. So I'm going to talk a little bit to speed testing and the things that we do wrong. This is a link is here, a brand new Wi-Fi device where someone was so proud to achieve that perfectly flat throughput that you see in the first part there. And I looked at his plot and I asked him to get a packet capture. And he sent me the packet capture of the actual behavior of what he was seeing. And as you can see this slope here over the course of 10 seconds, the underlying latency of this particular Wi-Fi link grew to almost half a second, which means it would be unusable for normal text, normal usage. The core speed test thing that drives me a little nuts is that what's the average? At 2.5 seconds here, the average latency is 100 milliseconds. At 5 seconds, the average latency is 200. At 10 seconds, the average latency is 300 milliseconds. But the slope here keeps getting worse and worse and would extend off the side of the chart. So when I look at speed test results, there's too many averages over too short or too long intervals. Been spending a lot of time looking at the FCC broadband data. Core thing, survivorship bias. What triggered you to do a speed test? How many tests did complete? And a good statistic is actually a negative one. Who is not doing speed tests voluntarily? Those are the guys getting good service. And all of the speed tests don't run long enough for my taste. I have a feature request for all you guys designing really cool new network technologies to measure this stuff. Please measure in both directions at the same time. People do uploads and downloads. They have video cameras doing security. The network behaves very counterintuitively when you do tests like this. Routers run out of CPU, the network gets weird. Please, please, please add a simultaneous up and down test to all of your speed tests. And if I can get some more reference standards, can I benchmark your benchmarks, please? Can you benchmark them against each other? Recently, I am really happy. Thank you, Starlink Speed Test, for adding a wonderful new responsiveness benchmark. This is an actual simultaneous test of my Starlink terminal yesterday, where I got really awesome responsiveness numbers from it. Only 20 millisecond inflation under load according to their methodology. But simultaneously with that test, I was running another tool I use called IRTT, sampling on a 10 millisecond interval. And the actual behavior of this link, according to my methodology, peaked at over 400 milliseconds of latency, which is completely unusable for any metaverse application. One of us is doing this wrong. Please validate all your benchmarks and your methodologies. And in fact, I've really kind of reached my limit. There's a thing called the Nyquist theorem. Those of you who have heard of that, please put it in the chat. Yes, I've heard of that. It's how we made CDs work. And the Nyquist rate for measuring voice over IP correctly is 10 milliseconds. That's the sample rate. Video conferencing is a little higher, but settle for 10. It's good. Metaverse is closer to 2 milliseconds, and the data center is closer to 10 microseconds. It's not 100 milliseconds. It's not 1 second. It's not 10 seconds. It's not 5 minutes. It's not hourly. 10 milliseconds. Nyquist theorem. If all of us were to do our measurements based on that at that rate, you would see things you people wouldn't believe. I have a couple other new metrics I've been proposing. One's called distortions per hour. Another one's called SPOM. And just page load time. It's a good one. And the big thing that has been mentioned several times at this conference is the ability to do continuous in-band measurements at the ISP and at CPE. Before I get to that, just an aside, I love CDF plots. I know nobody else does. I have a lot of tools. My stone knives and bearskins. My go-to big tools are IRT, and Flint. There's a new one that came out from Broadband Forum called that one there, Obudst. Another one called Crusader. It's written in Rust. iPerf 2 has a whole bunch of great tests in it. And good old T-Rex, run that. Kathy Nichols' work on listening to networks has had a huge influence on my work for over 11 years. I live and die and breathe inside of Wireshark to analyze deeply latency and network problems and everything. I've also worked very hard on producing systems that try to produce steady flow throughput, mostly using fair queuing technology. And they're pretty widely deployed today, and they're pretty good. I recommend people read RFC 7567, but add fair queuing to that. The working group could never decide on fair queuing there, and I just do that. And there's a lot of people doing middle boxes to help the ISP do the analysis and shaping portions better. How am I doing for time? I think I'm doing good. So another thing that I'm pushing for people to try to do more is just validate the simplest possible scenario against your device and network. A single TCP flow has well-defined behaviors at any given round trip time at any given bandwidth. You should be able to produce repeatable results against any gear, including buffer size or the AKM technologies, if you just test that. But you got to test long enough. You got to test till the time of the first drop or mark. A couple drops will get you a better number, and you might have to wait a really long time, but you will finally get a result that is accurately representing the characteristics of the network. I'm also a big fan of staggered start testing. I'm cheating. I'm giving you the answer to one of my quizzes here. This is what slow start looks like. You have that initial burst that saturates the queue, 500 plus packets in length here, and then it settles down to a sawtooth. Imagine millions of those happening every day, all impacting your network. I put a lot of links. Sorry, Bjorn, I didn't find the link to your thesis. I'll fix that. I really do recommend anyone diving deep into this technology to look at what's happened before it. These are some of the better papers that have gone by in the past few years. Or just Google for buffer bloat on Google Scholar. So in conclusion, and I hopefully have time to fit in quite a few more slides, if you can build tools that engineers can relate to, as well as users, you'll be making progress. As I've been pushing 10 milliseconds intervals for doing your samples, the Nyquist rate. Think about VoIP and video conferencing applications as hard or harder than you think about web traffic. Keep improving the transports. I'm a huge fan of seeing fair queuing algorithms become predominant across the internet. Glitches per second, glitches per minute. When a single conference like this, and I hope I've been good this whole time, has a pause in it, that's something that users perceive. And try to create a Rosetta Stone for whatever your benchmarks means. So bandwidth is not speed. Latency matters to get good bandwidth. Network transfers are bound by the physical round trip time, serialization delay, queuing delay, and retransmits. Today's network does congestion control via packet loss and RFC 3168 ECN marks. And every potential bottleneck can use an FQ plus AQM queuing algorithm to reduce queuing delay, absorb transient shocks, and reduce or eliminate packet loss. bunch of RFCs, but that doesn't help enough. Do I still have time for 3 minutes on this side? My life, Jorn? You want me to stop and take questions?
Go ahead.
All right. I've seen things you people wouldn't believe. Packets on LTE going 6 times around the planet. Great bandwidth on Wi-Fi, yet completely unusable jitter for VoIP. I've seen people use 240 megahertz wide Wi-Fi channels with enormous noise floors when they should just use a 40 megahertz channel that doesn't interfere. Far too long queues without signaling or flow queuing. It could be handled with 1024 checkers, 64 bytes each, all working for free. I've seen single flows with infinite queues at 100 megabits. I've seen billionaires building home routers out of 12-year-old obsolete software filled with buffer load, dozens of CVEs, and unable to handle IPv6. I've seen network collapses over time and distance. This is a favorite plot of mine. It's part of a blog post called Drops at Juniper. You can see cubic degrading over time because of the congestion collapse inherent in a 250 millisecond long queue. I've seen queues that are so much bigger than 250 milliseconds that I imagine that almost no traffic is really getting through. It looks busy, but it's not doing anything. I've seen attempts at outreach, reach all the gamers, but not the C-suite. Seen multiple specifications, lacking implementations or testing. And I've seen tons now of broken AQM code, despite the standards we published. In this particular case, this is the Pi AQM, same code, we thought. The Linux implementation is correct. I got no idea what BSD is doing. And of late, I've been working really hard on trying to improve the NTIA's broadband standards. FCC wants 120 service for everyone, and that's great, except that the most 100/20 services I've seen from the cable industry have 800 milliseconds of buffer bloat built into them. And for 11 years, I've been able to reduce it to about 5. Still, all these things will be fixed. Time and more tears on the train. Anyway, thanks for letting me fit in those 18 extra slides. Questions?
Thank you very much, Dave. Yes, we do have a few questions here. The first one is, why don't we see a drop in throughput in the slide where the latency has a ramp response? I think it's the one where you said it'll continue off the edge.
That was cool. More buffering than about 250 milliseconds is actually at a distance is actually incredibly damaging to TCP. You get into a feedback loop, a congestion, almost a congestion collapse scenario, where you end up losing a packet eventually, and then having to retransmit more packets because it couldn't figure out when it did. It ends up retransmitting more and more and more packets, and you see your throughput, your goodput drops, but you're still transferring the same thing. There's a link on the slide there to that particular test. Feel free, please, to reproduce that test for me. Next.
Cool. Yes. So next question is, what's, in your opinion, the best tool to quantify latency?
Flint is my favorite go-to tool. There's 110 tests in it, and it's the best active measurement tool we've been able to design in a decade of working on this. It's open source, available for Linux. I would really, by the way, welcome a Windows port for it, as well as someone putting it into a container. Recently, I realized that our goals in bare metal testing had everybody else had gone to virtual machines, and we hadn't tested virtual machines all that well. And this Chromebook we're talking on actually has really bad buffer bloat. So what else do I got? Oh, well,
right. Yes. Next question is, any recommendations for good tools for traffic simulation or traffic generation?
Well, I listed a couple. Believe it or not, T-Rex is a great tool. More people should learn how to configure that. It really helps on that. Inside the kernel, there's TraftGen for Linux. And then again, we use the Flint tool to generate. Flint is good to about 50 gigabits. And then after that, I don't know the right answers. So if that, hopefully that helps. But that's just load. I really, there's another standard called STAMP. And instead of STAMP, we built something that's much higher resolution and more portable called IRTT, which is in Go. And that one works all the way down to a millisecond. And that was one of the plots you saw. The things you can see if you sample at a millisecond about Wi-Fi and LTE are, I've seen things you wouldn't believe. So please give IRTT at a very fine grain resolution a shot. It's fascinating, even unloaded.
Right. Thanks. Thank you again, Dave, for an excellent
Can I do
talk.
an intro? Thank you. Can I do an intro to tubes?
You can, yeah. Go ahead.
All right.
Next
I love
speaker.
what Cloudflare has done to reduce physical latencies across the internet. Okay. And the theme of my talk is that once you have enough bandwidth, that's all you need. Africa does not have enough bandwidth. And it has really enormous RTT, something like 90% of all traffic has to leave the country. And the best way to fix that is to deploy better CDN technologies. So over to you, Tubes. Thanks.
Oh, thanks, Dave. Hi everybody. I'll start presenting my screen now. I'm Tubes. As Dave mentioned, I am from Cloudflare. I am a product manager focusing on network and interconnection. Let me know you can see my screen.
Screen is working.
Oh, fantastic. All right. So as Dave said, I'm from Cloudflare. I'm going to talk to you about why you need a CDN, because you need a CDN. We're not going to talk. Although I'm from Cloudflare, I'm going to refer to CDNs kind of in general and use the word we. I recognize that Cloudflare has some competitors. This is not a sales pitch. I'm not trying to sell Cloudflare to you. You may choose Akamai, Fastly, Bunny, Google, Amazon, whatever works for you. You should feel free to use. But this talk is basically geared towards, you probably need a CDN in general. And there's probably a lot of stuff that we do that you may not know about, or you may just kind of take for granted. And we're going to talk about that. First, we're going to kind of level set on, some kind of high level questions like why should I care and metrics, and then we'll get into the good stuff. So why should we care? Like, this is actually kind of like a very fundamental question. Why are we here? The answer is because if you're an application developer, and I'm guessing that probably some of you are, latency has a direct correlation to revenue. This is not new information. Amazon found this out, over 10 years ago. Google found this out in 2006. Stockbrokers have known this forever. If you've ever had any conversation with any tech company that deals with the finance industry, they have very, very strict latency requirements because they can lose a lot of money if they are slower than their competition. And so basically, if you're an application developer on the internet, you care a lot about latency. And that's not just true to application developers, and users care too. Some people like me and Dave Tot just want to be able to play music with our friends on Zoom and not have it be super choppy and stuff like that. So there's lots of applications for latency to end users as well. But the idea of like latency and network quality hasn't made its way to the C-suite, as Dave said. It's getting there. We know latency is important, and they know latency is important, and enterprises know latency is important. And hopefully by the end of this, you will recognize that it's important and you want to do stuff to be faster. When we talk about latency, we have to talk about what metrics matter, because different things matter for different scenarios. And we talk about RTT and we talk about network level metrics, but applications don't really care about RTT. They care about larger components. So let's walk through kind of different applications. Web-based content is generally going to be first contentful and last contentful paint. For those of you who are unaware of what that is, first contentful paint is how long it takes to start loading a web page, and last contentful paint is how long it takes to finish loading a web page. And that's super important because last contentful paint contains more than just going out and grabbing info from a web server and downloading it. It's also about rendering. If you have content that's rendered in series as opposed to in sequence, you may be faster. If you have pre-rendering, which is some new technology that Google is developing, then you may actually get faster. So applications and things that have lots of images and content to render kind of statically definitely benefit from not just raw network components and how fast you are on your server, but how fast your browser can actually render stuff is important. API-driven scenarios, Netflix streaming is inclusive. Don't really care about necessarily static content. They care a lot about how long it takes to return information. And for that, we use response, which is a W3C timing. It's comprised of connect, which is RTT, SSL, which is TLS establishment, DNS, wait, load, and send, which are basically DNS resolution. Wait, load are basically how long it takes to fetch the content, and then send is how long it takes to send it back. W3C timings are public. Pretty much every application uses them. If you're not using them, you should start. If you are using them, awesome, great, we're all speaking the same language. Video chat and RTC applications, that's where a lot of these conversations around RTT and packet loss and jitter start to really matter, because we're talking about SIP. And SIP is not an HTTP-based protocol, although some applications that use video and RTC use web, not all of them do. So generally, when we think about latency, at least from a CDN perspective and from a network as a service perspective, we think about kind of the lowest common denominator. What's the thing that's impacted most and looks the worst? So SIP is generally kind of your gold standard for that, because whenever you see whenever you see jitter or latency spikes, your SIP performance just goes down the toilet. And finally, gaming is RTT. That's really what it's going to come down to. Some game engines use web-based services, so they'll use WebSockets, or they'll just use HTTP. Some game engines use custom-based UDP stacks, and in that case, they probably have their own network performance kits built in. So they may not be able to leverage HTTP-based request logs like everybody else does, but they definitely have some notion of what performance looks like. So now that we're looking at all the different metrics, we got to look at where to look. I think Peter left a comment that said average isn't really good, and I would 100% agree. Average is average. It's not good. It's not bad. It's just kind of okay. Generally, we look at 90th percentile to start, and we'll go up as high as we can get. We typically don't go higher than 95th percentile, especially when it comes to metrics that have a very high dependency on the last mile. And that is because, as Dave showed, there are a lot of weird routing, things that can happen on the internet. You could have packets that go 9 times around the world, and that's not necessarily an application problem. It's really a packet delivery problem. And for network performance, you definitely want to look at both. And for, networking, we definitely want to see that if we can. But when we're looking at overall performance across, hundreds of millions of users, we want to solve for as many as kind of can be lumped together. And 90th to 95th is kind of where we live in that. For LCP, so last contentful pate and response, 90th is a good starting point. And we definitely recommend plotting all the percentiles that you can plot. And what you'll start to see is kind of an inflection point that basically means that we're starting to get into outlier territory. And you want to kind of stop measuring at that point and then just look at whatever percentile that is. The higher you can get, the better. And then performance is iterative. So you solve that problem and then you look and see what's the next step and next step and next step. And that's kind of how, at least Cloudflare and everywhere I've been takes an approach to performance, that we get what we can get and we kind of continue to iterate and get better. So now that we've aligned on why we're here, what metrics we're looking at, and what percentiles we're looking at, let's talk about what a CDN is. This is just kind of general stuff. Content delivery network. We deliver content. As Dave said, CDNs need to have lots of points of presence. We need to have lots of bandwidth and network capacity to perform our jobs effectively, which is coincidental because as an application developer, you also need all of those things, which is a nice little coincidence. That's because CDNs tend to sell to application developers. And as such, CDNs are a really good way to democratize growth. Network CDNs and CDN technology, we're very invested in a lot of the things that are being talked about. We've had conversations about L4S, AQM, and we'll talk about some of the other stuff that we do, kind of higher level up at the application stack. It's in a CDN's best interest to make sure that you're as fast as you can possibly be, because your success is our success. If you do really well, then we'll get paid more because more users will use our stuff, which means you'll pay us more, It's a great, nice symbiotic business relationship. And a lot of CDNs will also bundle network performance technology with security and zero trust network access and DDoS prevention for security plus zero trust plus performance. So it's kind of like a nice one-stop shop to get the things that you need. But again, this is not a sales pitch. So the first thing the CDNs do is we deliver content, we cache. At the end of the day, the less stuff that you have to send over the internet, the better. If you have to send stuff from the internet over the internet, the closer you are, the better. So we want to get content as close to the users as possible so that we can reduce the time that it takes to actually deliver content. And we want to make sure that you don't have to go back to customer origin networks a lot. Uncached latency is a huge problem. If your cache ratios are bad, basically, if users have to continuously go back to your website and go back to your origin wherever it is, let's say it's in Ashburn, Virginia. If users have to go back to Ashburn over and over and over again, that can be a problem if the user is in Riyadh. Because not just because they have to go all the way back there, but if we have to establish TLS and SSL, we have to do three-way handshakes, we have high RTT, you're going to have a really bad time. Caching keeps everything close. If for some reason you have to reestablish TLS, we'll talk about that a little bit later. We make it nice and easy, we make it fast. Caching improves not just overall end-to-end latency, it improves LCP because a lot of CDN technology involves how we deliver assets back to your browser, to the user browser, in a way that is optimal and provides the best latency and performance. There's a lot of research that's being done into that. And it's probably stuff that you as an application developer don't really care about. You're like, I just want it to be fast. Like, I don't really care what order my JavaScript gets delivered, but CDNs care a lot. So stuff that we think about helps make your life easier. And another thing that CDNs do is optimize for shortest path dynamic routing. So, you're never going to be a case where you can host out your content on a CDN and just be like, I'm done. I don't need a website anymore. You'll always need an origin network somewhere. You'll always need an AWS or a self-hosted server or whatever. And when users have to go back to that server, they want to take the fastest path possible. The 2 points, the shortest path between 2 points is a straight line, but that's not how internet routing works. Like, internet routing, as many of us know, and as Dave showed, does not optimize for latency. It optimizes for packet delivery, which can take a really long time. We think of the internet as like this. On the Cloudflare blog, we talk about this. You've probably seen any variation of user connecting to a website and there's a straight line in between. That's actually not even sort of how it works. Usually there is some crazy path to get to the ISP, which sends to Cloudflare. And on the user side, we didn't even talk about Wi-Fi. So the user might have to go over the air to get to the Wi-Fi, which goes to the ISP, which goes to a CDN if you have one. And then there is some CDN technology that's applied to make it faster. And then you go back to the origin to get your data, and your data may be on the same place as where you're receiving origin traffic. It may not, it may be somewhere completely different. So you have to go get that data, return it all the way back. That's a really long way. And in aggregate, you get a lot of really crazy network paths, and like the internet is just like this mangled amalgamation of cables, and it's confusing as hell. And it would really be nice if there was some way it could be faster. CDNs can actually kind of straighten this out a little bit, because what we've seen is actually by adding that additional hop, in some cases, especially at higher percentiles, that improves your latency because you're reducing the dependency on the last mile. CDNs will often have partner POP programs like Netflix. Cloudflare's got one where we embed in last mile ISPs to basically get as close to the user as possible so that we can kind of untangle that ball of the last mile internet, get close to you, and then deterministically route back to where you need to be, kind of straighten that line out a little bit. A lot of CDNs offer services like this. For Cloudflare, it's called Argo. For Akamai, it's called SureRoute. I don't know what Fastly's is called, but they have lots of different options like that. Amazon's is called Global Accelerator. A lot of them, if they have private backbones, they'll use their backbones to really improve. A lot of network capacity and cabling goes into this kind of stuff. And you can do it yourself, but that's a real kind of pain in the ass. You don't want to do it. And that leads us to TLS negotiation, which is, fun fact, one of the most computationally expensive things you can do on the internet, because cryptography is hard, and it's even hard for computers. It takes a long time on the box. When I was at Microsoft and we were debugging performance issues, we saw that we were doing way too much TLS negotiation. So we rolled out session resumption, which is RFC 5077 for those playing the home game. That allows users to pass back a session key, which just automatically resumes TLS, which automatically resumes a TLS session, which removes the need to do TLS session negotiation. And it's annoying because it's not just, the computation that's a pain in the ass. You have to do a three-way handshake. You can't really bypass that. It's just kind of how we've implemented SSL today. And there are ways you can get around that. You can use 1RTT, which is, the security approved version of 0RTT, which is basically just one more RTT. Or you can use session resumption and automatically pass that stuff in. You can implement this yourself, or you can let someone else do it, because this is, again, the business model of CDNs. This is stuff that you definitely can do, and there's really nothing stopping you, but you don't want to do it if you don't have to. And that really, and you don't want to, you could do it, but you shouldn't have to, is really kind of the modus operandi for peering. Peering is hard. It requires a lot of finding the right people at networks, getting the interconnections, deploying to certain internet exchanges, deploying to data centers. You got to have NOCs, you got to have operations, you've got to get you've got to get your ISP embedded models, you've got to get into those last miles as deeply as possible. Like as Dave said, Africa is a really big example of this. You can't just set up in an internet exchange in Kenya and expect every single African ISP to connect there. That's actually not how Africa works. A lot of African ISPs won't talk to each other, so you have to embed in every single African country, which takes a long time and takes a lot of money and takes a lot of lead time, which you could do. There is literally nothing stopping you from going out and building your own network. Just costs money and time. And oh yeah, you've got an application to build, which you no longer have time to do because you're focused on building a network. A lot of CDNs have kind of done this already. So you don't need that. And also a lot of CDNs have really good business relationships, can get embedded in these networks or are already embedded in these networks. So basically kind of have done the legwork for you, so you can just onboard to a CDN and kind of go from there. The summary here is basically that, right? Like, why would you do this when someone else has done it for you and you can leverage that? And that's really kind of a big thing. All of the stuff that we've talked about, RPM from Stuart, HTTP3, L4S, AQM, 0RTT, all of these are either in progress and being worked on at CDNs or have already been deployed at scale for a lot of CDNs. So like you should definitely, invest in these, and you should definitely think about this stuff, but this is stuff that, CDNs in kind of general are very, very invested in, because remember, your success is our success. A CDN is, built, and its business model is designed around ensuring that application developers and end users have the best experience possible. And you could obviously build your own network and do this, or a CDN can just do it for you. A lot of latency benefits, a lot of performance benefits, all of the stuff that we've talked about is being investigated or has been deployed again. So a lot of really good work that we're doing, and all the work that we're doing is super important to improving last mile connectivity. We're definitely supportive of that. We want to make it work. That's the summary, and that's actually it. That's the last slide I've got. So I think, Bjorn, we got some questions.
Excellent. Thank you very much, David. So yes, we do have a question, or a couple of questions. First one is, isn't TCP TLS session resumption vulnerable to replay attacks, just like TCP 0RTT is? Or does session resumption use 1RTT and then start exchanging data?
So there are definitely some replay attacks, that especially with 0RTT. 0RTT is the really big one that's susceptible to replay attacks. That's why 1RTT is kind of like the least or the fastest security approved. There are definitely other things that there are definitely like other ways you can do it. But yeah, like at the end of the day, it's going to come down to what you feel comfortable at. Like you don't have like the really great thing about CDNs and stuff like that is that it's not like you have to turn it on. A lot of places have it so that you can configure how you want it to meet whatever security requirements you have. So there are some customers who we have that definitely use 0RTT, and there are some customers that don't. So, you know, if there are stuff that's susceptible to replay attacks and stuff like that, like we support that, but we also support your desire to not use it if you need it.
All right, thanks. I thought there was another question in the chat. But no, I think it's the same question. Yes. All right. So I think unless there are any other questions, I would like to once again thank David. Great talk, and I think it's a very good way to end today, because tomorrow will be about how to commercialize and deploy low latency solutions, or solutions that either benefit from or contribute to lower latency. And you gave us a really good introduction to that, I think. So with that, we're finished for today, and I hope to see everyone back tomorrow. Goodbye, everyone.
That was great. I know you just hung up on everybody, but I just wanted to ask, my video actually came through on the satellite? It wouldn't have worked 6 months ago.
It worked pretty well, yeah. There
Damn.
was, I think there was maybe like a couple of times where there was like a glitch,
Good. Okay.
but
I wanted
no more
capture.
than twice, I think.
Wow. Okay.
Yeah.
Certainly 6 months ago, Starlink would not have been that good.
Oh, they've done something then. That's cool.
I don't know if they're listening to me. They shortened their uplink buffers.
Yeah.
It's better.
Very good.
But,
Glad to hear that.
yeah. So thanks for having me, and it's been a great conference. Have a
Yeah,
great
this is
day.
great. Thank you. Thank you, Dave. See you tomorrow, guys.